Hello again. So in this lecture we'll look at covariances. Now the idea of covariances may be familiar to some of you. It's just a measure of the relationship between two variables. So the way it works out is this. We take a look at the covariance between two random variables x and y. We write that is co of x, y this way. And it's worked out by take the random variable x and subtract its mean first. Take y and subtract its mean. Multiply the two together. And then take the mean again. This looks like it's a complicated thing. But we'll see in a second that it can be made easier. So let's first of all go straight to the next slide. It works out that covariance can be worked out simply by working out e of x times y and then subtracting from that e of x times e of y. Or if you like, e of x times y minus the mean of x times the mean of y. I won't prove it, but those interested can look at the proof. It's just simply using the properties of expectations. There's a formula here. To work out covariance means work out the mean of xy and then take the mean of x times the mean of y from it. An example will help us understand what's going on there. Here's the example, simple, x's and y's there. So let's take a look at the sums across here. So the values of x across here, so this will be the probability mass function for x when I add across the rows here. That's 0.4 and that's 1.2. The whole thing should add to 1, so that means this is 0.6 so far, and this must be 0.4. And so the question says, first find the value of C. Well, if this is 0.4, there's 2, 3 here, C should be 0.1. That's just the first part. 2, 3, this is 0.35. That's 0.4, and that's 1 to 0.25. So the whole thing adds to 1 as we expect it to. So here, because I'm adding, this is the values of y is over on the top, down here I'll get probability mass function for y. So to work out the covariance, first of all require the mean of x and the mean of y. Let's start working this out. So the mean of x first. The 0 can be ignored. So essentially the mean of x is going to be negative 4 times 0.4 plus 0 for the, so negative 4 times 0.4. The 0 gives me 0 and I multiply with 0.2 and I get 5 times 0.4. So I do the sums over here. Let me check in my numbers. You'll find that's 0.4. Likewise, if I work out the expected value or the mean for y, then it's going to be now the values for y times the probabilities. So it's negative 5 times 0.35. Again, I get 0 from this next one, and then I'll have 3 times 0.25. And that all comes to negative 1. Then I work out e of xy. So, as we said before, the zeros are our friends over here. So I know that nothing I get from here, because when I say x 0 times anything, that will be 0. And nothing I get from here either. So all I've got is these 4 entries to work with. Everything else is 0. That means I've got negative 4 times negative 5 times 0.2 and then negative 4 times 3 times 0.1, and then I'll have in the bottom row it's 5 times negative 5 times 0.1 and then 5 times 3 times 0.1, and if I do my calculations here I'll get that's 1.8. And so covariance between x and y is simply the exy minus the e of x times the e of y. So it's 1.8 minus, and I'll have 0.4 times negative 1. Be careful because the minus times the negative here becomes plus. So I'll get from here 2.2. So that's how simple the calculations will be in practice. You expect to find lots of zeros in the table, so that makes your work easier. But all I've done here essentially is one calculation for the mean of x, one calculation for the mean of y, and essentially the e of xy was just 4 numbers to work out. It's not very difficult to do in the end, and that's how it will be mainly in practice for us. Now, here's another important idea, which is independence. So independence essentially in this case translates to saying, well, if x and y are independent, I get some simplification. The first thing is e of xy becomes simply e of x times e of y. Now that's simple because if I know x and y are independent and I work out e of x and e of y, I already have e of x times y. It also follows that because if that's the case, the covariance is 0, because you see my covariance was e of xy minus e of x times e of, well, it's e of xy minus e of x times e of y. By independence, this part is simply e of x times e of y. So you can see I get 0 very easily from here. So independence means covariance is 0. And that's really an important concept. Now, important note here is that the implication works only one way. If x and y are independent, then covariance is 0. But if covariance is 0, then x and y aren't necessarily independent. To check for independence, in this case, if I know covariance is 0, I need to go back to my old idea and check that every entry in the probability table is going to be found by multiplying the row total and the column total. So be careful with that. And I've got an example over here. In this case, I find that with calculations you can find that easily e of x is 1.3, e of y is 0, and e of xy is 0. So the covariance will be 0 by calculation. But next and y are independent because again I look at the 0 entry that isn't found by 0.3 times 0.2. It doesn't work out like that. So clearly here the random variables aren't independent, but the covariance is still 0. If I do know, however, the random variables are independent, I know covariance will be 0, and that's what simplifies things. Properties of covariance, I don't want you to take too much stress over this and try and understand everything here. We'll just go through the important bits. The first is the covariance is symmetric. You expect it should change the order here, makes no difference. This next one is important, that the variance of x is found by covariance of x with itself. And there's some scaling things here. If I multiply by a and b, all that happens is the scale factors come outside here. Exactly the same with the variance. And if I've got sums happening here, then things break up in the usual way with sums. So with x plus y with z is just x with z, then y with z, and I add covariances up. You can look at the proofs if you wish. I won't bother with them for the moment. Those interested, look at the proofs, please. Now, as an exercise over here, just for practice, if I'm looking at covariance of, say, 2x plus 3y and x plus 2z, the way it works out essentially is I'm going to put 2x and 3y there, and then the x and the 2z there. What I'll get over here in this table, here I've got 2x and x, and here I've got 3y and x, and here I get 2x and 2z, and here I get 3y and 2z. So you can see what's going on here. I'll have covariance for each of these things. So that the first one is here, covariance of 2x with x, and the next one is covariance of 3y with x, and then I get covariance of 2x with 2z, and then I get covariance of 3y with 2z, and that's essentially what I have over here. So you can put the thing together in this kind of table if you wish, and then all that happens is the numbers come outside. So the 2 comes outside and I get twice covariance of x with x. And the number here is 3, so I get 3 times covariance of y with x. And then I get, again, the number comes out here, and I get 4, the 2 and the 2, times covariance of x with z. The 3 and the 2 come out, and I get 6 times covariance of y with z. And I can collect terms if I wish. So I've got y with x and y with z and x with z, they're all different. But the covariance of x with x, as I saw earlier from my rule, is variance of x. So you can see what I've got over here as my result in the end, is I've got twice variance of x, and I've got 4 times the covariance of x with z, and I've got 3 times the covariance of y with x, and 6 times the covariance of y with z. So that's how this works. You can, as an exercise, try and simplify this one by putting the thing in the tabular form as I had over here. Some main results here, sums for random variables. And we'll see that in the next lecture.